Okay, welcome everybody. So the plan today is to speak briefly about SLT 40, which is a brief note that I finished over the last week, following on from the discussion last week about inductive biases and SLT. That's by no means a finished document, but there's a version on the Discord if you want to take a look. So I'll speak about that for 30-45 minutes or so, I hope, and then we'll do research updates as usual. So I'll start over here and just remind you what we spoke about last week as part of the motivation for what's going on. So last week we spoke about some of the literature in the AI alignment community speculating, I would say, on the influence of inductive biases in training neural networks on safety properties. Inductive biases being the kind of solutions that your optimizer will tend to find given the algorithm you've chosen and the data you've chosen. So in a Bayesian setting, we would say the kind of solutions, the kind of parameters that the Bayesian posterior will prefer. And then you can try and argue about that using things like notions of simplicity or speed. And then we discussed last week how various people have ideas for why preferencing algorithms that are simpler might be safer, because an algorithm might not go and do all sorts of unintended things that are baked into the data distribution and the reward, say, but which you didn't intend if it doesn't have enough bits to represent those naughty processes. It might also not go and do bad things if it doesn't have time to execute those naughty processes. So that's a very cartoonish representation of the arguments of the relationship between inductive biases and AI safety. What I want to speak about today is a kind of commentary on, I suppose, the way people tend to think about simplicity in this context, and mostly, as usual, I'll be speaking in the Bayesian context, and so I'll just say the caveat up front that the translation of any of this to be speaking about the actual behavior of networks trained by SGD is an unknown step. So I won't address that. I'll be speaking purely in the Bayesian setting. And nothing that I'm really going to say today needs the AI safety kind of application for its value. It can be read as just a sort of pure SLT comment on the nature of degeneracy and how to think about it. But given that we spoke about this last week and the fact that it's here, I'll just make one comment, which is that people still tend to think about the inductive bias that sort of embodies Occam's razor as being about description length or number of parameters or something like that. I mean, that's, as we know, an accurate intuition in the case of regular or minimally singular models. We know it's a false intuition in general, but that sort of remains, I think, for most people, a pretty technical objection, right? So it's like technically that intuition is wrong, but there isn't like so much replacement intuition for, okay, suppose you were to give me two algorithms that use the same number of bits in their specification or the same number of parameters if they were, to be presented as like a minimal neural network or something. You're telling me that these two algorithms, which look the same to me in terms of complexity, in terms of how many bits they take to specify, those two algorithms, you're saying one could be nonetheless very much preferred by the Bayesian posterior in some loose sense than another, due to somehow being more degenerate. But like, what is that possible extra degeneracy? Is there a way of thinking about it that it must be somewhat different to the number of bits it takes to specify the algorithm? Okay, so that's what I want to speak about, is exhibiting, not in the case of neural networks, but in a slightly different setting, exactly a way in which there is a computationally intuitive sense in which you can be more degenerate and therefore lower complexity, even though you're sort of using the same or more bits. Okay, so we'll move over to the other set of boards for the rest. Any questions about that preamble before we get started? All right. So this is titled Complexity Beyond Parameter Counting. So I want to start with a sort of high-level idea, which is part of the motivation behind the developmental interpretability agenda, or just in general the attempts to link geometry to sort of science of deep learning, at least the way we're doing it. So the high-level idea of let me think about this for a moment. So the high-level idea is, given a parameter, and I'll just adopt our usual notation. So given a parameter, say a neural network, the idea is that the local geometry of the pair, consisting of the KL divergence, has an analytic function at the point. So such a pair is often called a function germ. So by this I mean the behavior of the function arbitrarily close to W star, K being the KL divergence between the truth and the model in the usual sense. The idea is that that geometry reflects non-trivial internal computational structure. Of the model W star. I put scare quotes because, strictly speaking, that's nonsense, right? I mean, the model is just the probability distribution, Px or Py given x, comma, W star. That's just a distribution. It doesn't have any internal structure, right? But for many of the models that we have in mind, we know more than just this distribution, right? It's not like someone hands us this table consisting of pairs of, W stars and like the parameter function map. It's like this is given to us as a table in some sense. We have an algorithm typically that will compute for us a probability of a given sample, right? So what I mean by structure is the structure of that thing which is standing behind the probability distribution as a function. So the algorithm that computes that function, for example, the neural network. Which certainly has internal structure, right? Circuits and so on. Okay, why would that potentially be the case? Well, the idea here is that small changes in the parameter near W star lead to small changes in the distribution. That's of course the whole point of the Fisher information matrix, but the Fisher information matrix is just the Jacobian of the parameter function map, and that's a very small piece of the geometry of that function. There's more, and indeed we know we need to pay attention to more in SLT. But anyway, there are small changes in the distribution, perhaps captured at first order by the Fisher information matrix, perhaps at higher order, and those small changes of course feed through to small changes in KW, which is the KL divergence of some fixed distribution to this thing that is varying. And those small changes in KW, roughly speaking, is what we mean when we're talking about the geometry of K at W star. Okay, well, hiding in between here are small changes in the computational process, which produces PXW, and therefore whatever small changes in that probability distribution are captured, say by the Fisher information matrix or some higher order thing, arise from some small change in the way you computed that thing. Now, in a neural network, we might have in mind that that might be some particular circuits turning off or turning on, being broken, being made to work. I don't really want to suggest any particular idea, but this is the link, potentially. Okay, so what would a small change in a computational process mean if the computational process were not a neural network but something more familiar? So this is where this kind of geometry of program synthesis idea, which a few of you are familiar with, comes into the story. And the idea here is basically that if you perturb a Turing machine by introducing errors into its execution, I'll be more precise than you may want in a moment, but I'll be vague for now. The pattern of the way that the outputs change reflects the structure of the Turing machine, whatever that means. And is also captured in something like this story on the left-hand board, as long as you can put Turing machines into some kind of framework for which it makes sense. That is, you would need to have a parameter space in which Turing machines are points, such that small changes in the parameter can be thought of as introducing errors into the execution of the Turing machine. Just at this high level, what I want you to sort of reflect on is whether you believe the first idea that the way in which the output of a Turing machine might change if you somehow introduced errors into its execution might be reflective of the structure. Okay, obviously it's quite vague so far, but if there are any questions, then I can answer them. I'm just looking at the document and trying to decide what parts to say. Okay, maybe I'll make some general remark on the role of error correction in computing. So, of course, this goes back to the very beginning of trying to construct computers that execute, in the physical world. There's a famous article by von Neumann which treats trying to build reliable computers out of unreliable parts. In that situation, he's speaking about automata, each of which automata being built out of sort of individual pieces. There's a finite small set of pieces which you can plug together in many different ways to build a general machine. If you consider each piece to have some probability of error, you can try and consider means by which you can produce a machine which computes reliably for some period of time, even though its individual components have some probability of error. You can do that for Turing machines. Indeed, it has been done. So there's really nothing special about Turing machines in the following discussion. It's just a framework that I find natural. But you should substitute, in the following discussion, you should just substitute Turing machines for any model of computation which has the following kind of character, where you can imagine sort of a relatively flat way of specifying different computations to be done. In Turing machines, that would be specifying codes for a UTM. So it'll be important that you have a bit of a working knowledge of what a UTM is. A UTM is a universal Turing machine. So what I'm about to explain is what this means. So how do you introduce errors into the execution of a Turing machine? There's a few different ways. Roughly speaking, it just means that you introduce... so a Turing machine is a bunch of rules for what to do in what situations. The situations being where there's a tape with some number of squares. The entries on the tape are from some alphabet, and the Turing machine is looking at a given position on the tape with a given state. Okay, so the transition function of a Turing machine, often written delta, says if you're looking at symbol sigma and you are in state Q, you should write state sigma prime, you should transition to state Q prime, and you should move left, stay where you are, or move to the right. So right, new state, direction. So I hope it seems relatively natural that if you were to perturb or introduce an error into the operation of the Turing machine, it would be to somehow have the output here be a random variable, right? So that if you were to see sigma q, then you might, with some small probability, instead of writing sigma prime, write something else. And that's indeed what I mean. Now, you could talk about it in terms of the transition function and the outputs being a random variable, or you could talk about it in terms of a UTM simulating this machine and having some probability of thinking the transition function is something that it isn't. And it's not identical for sort of technical reasons, but I think for the purposes of our conversation today, pretty much the same. So to introduce error into the execution of a Turing machine M with code C for a UTM U. So the code C is just a way of writing down the transition function delta. So delta is the transition function for a particular Turing machine. Each Turing machine, in some sense, the Turing machine is that transition function. So maybe I'll write delta sub M. So for M, So the UTM is often thought of as a, doesn't have to be, but often thought of as a multi-tape machine, and there's a description tape, and on that description tape there are many entries. So maybe I'll change my mind. I'm just trying to write down an encoding of the transition function for a given Turing machine. I'll just do it like this. So sigma 0, q0, sigma 1, q0, dot dot dot. So sigma 0, sigma 1, dot 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 are tape symbols, q0, q1, dot 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 are states. And then here I'm going to put well, the sigma prime q prime d from the previous board if the transition function for m said for this particular pair you would get sigma prime q prime d, and then so on. Right, so these before it was just a function, some mathematical object, but now it's actually symbols on the tape of a particular machine, the UTMU. And once we put that description on the tape and we put on the work tape some sequence of symbols X, and we put on the state tape, strictly speaking these are encoded, but I won't worry too much about that. We put here some Q. I'm conflating the states of the UTM and the states of the machine. All of these are details. Okay, so to simulate the machine M, what we have to do is we put on the state tape the state we want it to be in, we put on the work tape the stuff that should be on the tape of the simulated machine, so that is this here. So that's sort of embedded into the UTM, and we put here the machine to execute, the sort of stored program, and then the UTM will chug along, and I need to briefly outline how it works for the error propagation to make sense to you. I'll just do this all in an overlay and erase it as I go, so maybe I'll pause here in case there are questions before I start doing that. So just for context, I want to tell you how to run a Turing machine M with some error, the error being a probability distribution on these spots, which say what probability of what kind of errors is the case. Once we know how to execute a Turing machine with some error, we can formulate as a statistical model that allows us to put it into the context of the left-hand board here. And then there's at least a potential link between the kind of structure of the Turing machine that gives rise to how it behaves with respect to error and geometry in the sense of SLT. And it's that connection which I want to state a result about. Okay, so it seems like there are no questions. So let me outline how the UTMU executes. It has a head. It has multiple tapes. So a multiple tape Turing machine has a head per tape. So here's the head of the UTM at the beginning. Okay, so it's looking at a particular symbol here and a particular state here. For simplicity, I'm just going to assume that I can put the maybe I won't assume that. Okay, so I'm simulating the state of the machine M. So the machine M is looking at X and is currently in state Q. Or it's looking at the first symbol of X, right? The first symbol on its tape. What should it do? Well, I need to consult the transition function delta. The transition function is written here. At the moment, the UTM can only see these three squares, so it can't decide what to do yet, but it can move to the right and try and match this pair against this pair. Right, so it's going to go to the right, asking the question, okay, does sigma 0 map with this? If so, it will move one hop to the right and compare this to this. And if it matches on both, then it's going to do something, right? It's going to look at these three symbols here, and it's going to do whatever they tell it to do. It's going to write a sigma prime, it's going to transition into state Q, and it's going to move this to the right, say, if that was a +1. If it doesn't match, it will move to the next tuple. Strictly speaking, I'm only going to describe what happens for a UTM of a very particular kind, which reads all the way through the description tape even once it's found a match. So it always goes to the very end and then loops back to the beginning. There is no single UTM. This is a particular choice which has good properties for technical reasons, but I don't think it's very important for today. Okay, so that's how a UTM works. It's going to scan the description tape and figure out what to do. So now let me describe how it executes when there's an error. Are there any questions about the normal execution first? Okay, so let me describe an execution trace when, let me see, did I have an opinion about which kind of bit it was? Not really. Okay, so suppose instead of a definite description, there was a probability distribution for the symbol to write. When you observe this sort of configuration sigma 0 q 0. Right, so let's suppose that that was 1/2. So I'll write 0 and 1 underlined for particular symbols in the alphabet that could be written. Okay, so how is U to execute? Well, to execute U with this, so we think of, I mean, I guess when it's a 1/2, it's not clear what's an error. That's you know, a typical issue. So let's say it's 1 minus epsilon. Just to make sure I agree with what I do later. Is that right? We imagine epsilon pretty small, so in this case it's clear that 0 is like what we're supposed to do, and the potential error is to write a 1 instead. If I were to want other kinds of error, I mean, the specification of the distribution here tells me what kind of errors are possible and what probability they have, right? So I get to specify the kind of error by putting a particular distribution here. So let's suppose that's the distribution. Okay, so what you do is every time the UTM reads from the specified entry, so this distribution is associated not to the symbol Q prime, but the position on the tape, right, which I'll mark with blue. So we're putting a particular error distribution here. Every time the UTM goes to read from that position, it samples independently from this error distribution. and then continues to execute as though it were doing its normal algorithm, but just happened to see that particular sample in that position. Okay, so the execution trace, which I'll write as mu, would just be the results of all those samples. And if you know which samples you get each time, so the UTM is designed in such a way, I'm going to assume that it is looking L times in order to compute the output. This number L, of course, depends on how long it takes to actually execute on this input. The machine may not halt, etc., etc. But for the moment, we're just going to assume this L is fixed. So there's a sequence of possible outcomes, determines the output. The output meaning what you see on the work tape in the usual way that you understand the output of a simulated machine. So if the work tape ends up with the sequence of symbols y, then you would say that y is u with the execution trace mu on x, and I'm just assuming this machine m is sort of fixed, and all I'm doing is introducing. It depends on the error distribution as well, right? So maybe also depends on the p. Well, no, it doesn't, because it specified the trace, right? Okay.
Question.
Yeah.
So the work tape is deterministic, then?
Correct.
Only
Once the execution trace is fixed, yes. But I mean, of course, its content are random variables that depend on the error distribution. Otherwise, yeah.
Right. But the error will only affect essentially what symbols get read from the description tape.
That's right.
Right.
Yep. Yeah. Okay. That's right. So you're asking that maybe when the UTM goes to read the work tape, it might also have this issue, but that is not the case. There's only errors once you've resolved the uncertainty on the description tape by sampling. There's no further uncertainty.
Okay. Yeah.
Okay. So that introduces the sort of now probabilistic model. So we can embed the UTM into an SLT context in the following way. We can take W to parameterize. Okay, what's going on here? My iPad's behaving strangely. Just one moment. So possible errors on the tape. I won't be more specific than that. The way it's currently sort of set up is that you just think about it as the joint distribution, well, just as a sequence of possible 1-bit error distributions. So you specify what possible error you would allow in the spots sigma prime, q prime, and d for all the different tuples. So for each tuple on the description tape, you have some specified error distributions for those 3 spots. Those possible choices parameterize a parameter space W. And then the model is, well, given such a sequence of possible error distributions, you can define P of y given x w to be the probability that y is the output given x with allowed errors w during execution of u. And there's a fixed number of steps involved here. The x's here also have some, so the x's are sequences, and we're assuming there's some true distribution of inputs. Okay, so that gives us our probability distribution. And we're going to also specify a q. So we suppose q of y given x is just going to be how should I say this? So suppose T is a Turing machine which halts on all x in sigma star. So the true distribution is just the output of this fixed Turing machine. Okay. So that's realizable as long as the number of tuples we're considering is enough to express t. And the statistical inference problem we're setting up here is the question of, if you were to observe a bunch of inputs and outputs from some particular Turing machine, which Turing machine was it? Right? So given samples xi, yi, I equal 1 to n, this distribution tells us in particular which Turing machines are more likely as explanations of that input-output pattern. And the geometry associated to this is, of course, that of the KL divergence KW. Okay, so what I want to quickly sketch is why that sort of gives rise to some interesting geometry. So the question that we sort of started with is, how can higher order degeneracies so for example, if w was a single variable, which is the case I'll restrict to in a moment, how does, well, maybe not that, given it's supposed to be non-negative, how does something like this arise? Okay, so I want to explain a property that a Turing machine might have, such that if you were to restrict the parameter space to be in an error distribution in a single position, as I was sketching earlier with the sigma prime error distribution. So think of W as being a variable which specifies that distribution, the epsilon, for example, right? One-dimensional parameter specifying the error distribution. K would be a function of that in the above setting. And I want to give you an example, I want to tell you as a theorem a property that a Turing machine M might have, such that in a neighborhood of its parameter, if you were to parameterize deviations from it by W or epsilon, it would have kW equals W to the 6, or plus higher order terms, which don't matter, so that it would have any order you like. Okay, so that's the theorem. So let me state the setup and then state the theorem. So we consider W restricted to be just 0, 1, i.e. specifying error epsilon in a single position of the description tape. So as before, right? So we think of that as that's kind of the situation. So then kW, so it's really k epsilon. And I need to make one definition before stating the theorem, which is what it means to have M. So maybe I should specify M. So the description with 0, so that is all these things out here in the description tape are fixed. These are fixed. This is the only thing in which there's error. If there's no error, that is if you sampled and got a 0, that's what we call the code C. And that is a code for the Turing machine M on the UTM U. Okay, so I want to state a property of M. It's really a property of the code, or the code UTM pair, but I'm going to state it as a property of M. We say it is robust to errors on a particular input X. Well, it's robust to S errors. If for any execution trace mu containing less than or equal to S ones, so remember sampling a 1 was an error, U mu X is the same as the output that M would have given on X, or that is the same as the output the UTM would give if it got the execution trace that was all zeros. Now, I could have formulated this without the UTM, just talking about errors in the transition function, and there would be a slight difference there, just depending on the way the UTM is set up, so I'm not going to pretend those are exactly the same. But there's many details here, and I don't want you to sort of get distracted by ones I don't think are particularly important. So you should think of this as being like one reasonable way of saying what M would do if it were to see errors. And I kind of outlined the precise sense in which that's the case by the execution of U. Okay, so I'm going to pause here for questions about the setup or the definition before I state the theorem.
I suppose one question, and maybe this is in the weeds, but when you the kind of naive thing that I would want to do to sort of propagate uncertainty through propagate these errors through the machine is like, oh, if I read, some particular action, it tells me with 80% chance, invert the bit I just read, and with 20% chance, keep it the same or something. Then I sort of just, if there's a 1 there, then I write a 0.8 basically, right? And then I sort of kind of linearly propagate. But it seems like you can't quite do that because there's like...
That's kind of computing on distributions or something. This model is more like the physical model, where it's just like the error process is like outside, right, and just intervenes and makes it so the channel between the description tape and the UTM CPU just happens to receive a 1 instead of a 0, and it doesn't, it's not aware of that or whatever. It's just like outside.
Right. Yeah, it seems like if you actually wanted to like compute the output distribution, you would have to like resort to like checking all possible errors
that's right
would happen. Yeah, okay.
Yes, that's also interesting, but that's not that's not really like, I don't think that's like more like probabilistic programming than runtime error sort of correction, I would say.
Right. Yeah, well, yeah, that's okay. Yeah, so it seems like there's a, like, if you actually wanted to compute this scale divergence, it'd be quite hard unless there's some sort of simplifying assumptions or the thing is very small.
Yeah, that's right. The scale divergence will be quite a complicated function. That's right. Because you need to propagate this uncertainty in this particular way. Yeah. Writing down that the actual formula for the scale divergence is more complicated than just giving this execution trace description. Okay, any other questions?
Okay.
All right, so let me state the theorem then. Okay, so if M is robust to S errors on here, maybe on all inputs X, then KW has order greater than S plus 1. That is, so really it's K epsilon the way I wrote it. So that is K epsilon looks like epsilon to the S plus 2 plus higher order terms. Okay, in particular, if M is robust to 1 error on all X, then K epsilon looks like epsilon cubed. Okay, so this, I'm not saying it is, yeah, I guess the way I wrote it makes it look like the order is S plus 2, right? I would just prefer to assume you know what order means. Let's say it like this. So that is right, the first s plus 1 derivatives all vanish at the origin in the Taylor series expansion. Okay, so this shows you an example of a degeneracy of higher order, so not of order, sort of looking at squares, that arises in the KL divergence, and it's that's a geometric property, right? Sort of tautologically. So the order of the function here is sort of basic geometric information about the pair, which is k, comma, the parameter, which in this case was k, comma, the code, or you could say the geometry near the Turing machine in parameter space for this particular choice of KL divergence. The order is a geometric property of that pair, and it's arising from this robustness to errors. The proof's in the note. I think I won't go through it. I don't have time anyway. But the point that is meant to be made here is that, so this gives an example validating the idea of a relation between sort of computational structure of M. Remember, I talked about computational structure earlier as being the thing that is behind the probability distribution P of y given x comma w. In this case, it's M. Maybe we're more interested ultimately in neural networks being behind a probability distribution. I don't know how this idea translates to neural networks, although obviously that's very interesting. It validates the idea of a relationship between this and the geometry of this pair. We had some examples of this, but they were like relatively trivial and at the order, like sort of at the order of the Hessian. And this is the first example I've thought of where I think this is a real connection. So I'm sort of much more bullish on this idea now. Maybe I should spend a moment defending the idea that the robustness to errors is in fact a computational structure of M. I think it is without question that the right-hand side, the order, is geometric information, but we could argue about whether this robustness to errors is computational structure. So let me spend 2 minutes defending that idea. First of all, let me attack the idea. So you could say, well, it's not structure of M, it's like about how U executes M, or rather its code, right? It's about this sort of environment in which M is executed. And maybe it depends very much on the UTM, and it's not really about M itself. I think that's a fair point. That is sort of related to the fact that the geometry on the right-hand side is a geometry of K, K being an auxiliary object that isn't like M itself, the Turing machine, doesn't come with this KL divergence. That's chosen and will depend on some choices. That's inevitable to some degree, right? There's no way of talking about geometry of a Turing machine that doesn't involve embedding it into some context. So to some degree that's inevitable. So putting that aside, why would I argue that this robustness to errors reflects computational structure of M? So partly this is intuitive, right? So if you introduce errors into bits that don't matter, then they don't matter. It doesn't change the output. So this generalizes the idea of bits not being used. If an algorithm M comes in the form of some kind of modular organization, then errors in different parts will have different effects. Another way of saying that is that you can more easily error correct for modular organizations than non-modular ones. This is quite an old idea. I posted a paper in the Discord which sort of is revisiting that in some respects. So that's not an argument, I suppose, for this link for a generic M, but rather you could by taking a given algorithm, set up an error correcting kind of shell for it, and arrange for it to be robust to errors, and therefore reliably drop its RLCT by having the order be larger. And if you were to do that, then that change in the RLCT you would be able to very clearly attribute to the augmenting of the algorithm with error correction. And if you could do that error correction by virtue of it being modular, then you would have a link between the modular structure and the geometry. And this is something that sort of seems natural, but I haven't had a direct path between modularity and geometry or dropping the RLCT before sort of seeing this. This is a very preliminary example, of course. So maybe I'll stop there and just say that this whole line of thinking came out of a conversation I had with Will at the Watanabe meeting. Okay, so I'll stop there, and any questions? Yeah, I should say it's relatively easy to so maybe just one comment on if you were to take the free energy principle seriously here, you could speculate that many naturally occurring algorithms will come with error correction because it's relatively straightforward to take an algorithm M, and this box is meant to represent its sort of tuples, or the information necessary to specify it. It's relatively easy to wrap that in a sort of small shell which executes M, but in a way that's tolerant to errors. For example, you can just execute M 3 times and do a majority vote, and then output the majority vote. That will give you robustness to one error.
How does that sort of counterbalance against the fact that you had to make the code like 3 times?
That's right.
Or I guess not necessarily.
That's a good question. So I didn't make the code 3 times bigger because I only had to specify M once, but there were some extra bits in this shell, right? So let's say that was like plus A bits to write the shell. And that robustness to error is going to there's some parameters here. So maybe that it was the RLCT contribution was like B on 2 if each one of them cost a half, and maybe now it's B on 3 because you corrected one error in each of them. But you also added the A. So there's some balance between the extra bits you specify to do the error correction and the drop that you get from the higher order in the KL divergence / lower RLCT. It's an open question whether or not you can get that to actually decrease it, but it seems to me, playing around with it a little bit, that it should be possible. So if that were the case, I mean, I'm not saying I know that to be true. I think it would be very interesting to establish. If that were true, then you could make a pretty general argument just on the grounds of the free energy formula that such error correction structure should, like in principle from a Bayesian point of view, occur pretty universally, right? Just because it's sort of like a free lunch to drop the RLCT by, if you have the bits available and you have the runtime sort of capacity. I mean, that's the other trade-off, right? Like, how long do you have to run the machine in order to do these 3 parallel executions? But it opens up a sort of interesting trade-off between runtime error correction, time complexity, RLCT, which I think is quite interesting.
And I wonder, so the kind of error correcting codes that I'm most familiar with are like at the level of data, like
Yep.
you correct some message from like bit flips, but like this seems almost more like computational kind
Yeah,
of
there's a standard approach
error
to.
correction.
I mean, there is a literature on runtime
Okay,
error-corrected Turing machines, which basically just applies the error-correcting codes to the tape. So you just treat
I see.
the message as the tape contents, and you just encode it on the tape. So then you have an encoding stage, a decoding stage, an operation stage, and you're just continually like protecting the contents of the tape from errors in the machine. Yeah.
I see. Although that seems a little more restrictive than this generic kind of sort of like run the algorithm 3 times kind of thing.
Oh, this three times thing is like the most dumb, simple form of error correction you might do. Yes, certainly. Yeah.
Right, but the point being that rather than like error correcting the tape and
Yeah, yeah.
like writing M 3 times, you run it 3 times instead.
Well, if you think about it, how are you going? I mean, if you have a single work tape, how are you actually going to do this? Well, you might interleave 3 copies of the work tape, one for each of the parallel streams, and then be writing to it, which will have like a little bit of the flavor of a kind of just having a code where you're just redundantly having the contents written out 3 times, right?
I see. It's only sort of that distinction is only important in the case where like you care a lot about what actually are the parameters and
Yeah, so there's a continuum where, I mean, if you do the majority vote just at the very end, that's one thing, but you could also do it like every 10 steps, right? And then you would be kind of treating the halfway houses. So like every 10 steps, you would kind of be treating the contents of the work tape you receive as a message from the past, right? And then you check to see if there's been any errors in it, and you correct
right.
them if there are, and then you continue for the next phase. So you just kind of apply the standard idea of error correcting signals to the work tape as a signal from the past.